Well, I'm gonna get started with this.
Yeah, this was after.
Are we recording yet?
I'm recording.
What?
I am.
Okay.
Why, you want to say something that I need to beep out later?
No, just not relevant to class.
Just not relevant. Okay, that's okay.
Here, read it quietly to yourself.
The thing is a week of classes. The week after that.
Oh, that's good. I like it.
Oh no. That's awesome.
I better not make fun of Jesus because the rapture is coming.
Yeah, that's
May 21st, marks the day.
No, December
yes.
21st, 2012.
Huh? It's May
December
21st. May 21st, is the day of rapture, and the May 22nd is the atheist, post-rapture party.
nice.
Yes.
Nothing relevant.
Nothing relevant at all. Well, it is relevant. It is relevant because if for people who will be picked up, on the day of rapture, they don't have to worry about their grades anymore.
Yeah, but that sucks because for the rest of us, we get to see how crappy our grade was.
You know why I like programming?
Yes.
I don't have to believe in God, I become God. The power to create and destroy in my fingertips.
No, that's playing The Sims.
Alrighty. Well, let's go ahead and get
That's more like
started.
being benevolent or malevolent dictator.
Yeah, that's true.
Okay, so I did finish grading, but I did not have time to post the grade. Okay, so it will be posted sometime tonight. It is all, it's all done. At what time? I don't start to work until 11 p.m., so it will be somewhere between 11 to 2 a.m. Yes.
Can we just skip lecture and sit here and watch you upload our grades?
No. Good try, but no. Okay. Okay, are you talking about pre-adjustment or post-adjustment?
Both.
Okay, post-adjustment, the class average is 60%, which is a high C, pretty close to a B, but not a B yet. A B is 62.5%, remember, the scale that I have? Okay, so after adjustment, the class average is 60%, which is a high, high C, or very, very low B, something like that. So I think that average is very reasonable, very, very reasonable.
What about before the adjustment?
The adjustment factor is 160%.
Wow. Holy crap.
Yep.
How many people scored 160%?
No one scored 160%, but quite a few people scored 120, 130%. So those people, have all that extra padding for the final exam. Yep.
So you're saying nobody got it 100% perfect?
Nobody did 100% perfect. Before adjustment. Yes. After adjustment, there's a whole bunch of people getting more.
You can't on his exams. The exams aren't relevant.
Okay. So are there any questions? Did you guys check the answer? Because
No.
I thought I posted the answer.
You did.
Yeah.
Can you give us the key?
Yeah. No, not the key. But I posted the decrypted version of the solution.
Why didn't you just give us the key and tell us to figure out how to use it? That'd be a valuable lesson.
Yeah, well, but most people won't even do it right. So anyway,
Their
the
loss.
answer is already here. What you can do is to compare that to your own answer. Okay, you can just kind of go through the whole thing. I will post exactly how it is graded. How many points I assign to which part of the correction. So all of that stuff will be posted. I will give you exactly what I use to look through your programs. To give you the number of points that you're getting. So all of that will be disclosed. There's no mystery of why do I get this score and stuff like that. It's just I need a way to disclose that information without having to copy and paste to insanity in the process.
So is that your spring break?
No. Well, my spring break was a little bit more busy than that too. I have to do yard work and drive the kids around during the day, and usually by nighttime it's already kind of tired. So I can't really do a whole lot of grading at night. So anyway, I think the class average is not bad. Okay, it does span from one extreme to the other extreme. Okay, so I'm not talking about 40-something people all getting around 60%. We're talking about everything from 130% all the way down to 0%. So it spans the entire spectrum. And the funny thing is too, well, I guess not funny, but it is interesting to note, is it's not a bell curve. We don't really see the bell curve. It's more like a camel. Okay, I see two peaks. Okay, one peak close on one side of 60%, and one peak on the other side of 60%. So it's a bimodal distribution. Yep.
Will you be providing a scatter plot for us to examine?
What?
So we can observe the curve ourselves and see what they
I
look
suppose
like.
I could. Yep.
Excellent.
Do we have video recording about the exam too or not?
No, there's no video, but this is a text file.
Yeah,
That's
because
the
I saw
solution.
the text,
Yeah.
I was wondering if you posted any video.
No, I did not. Do you guys want me to explain that? I mean, I could.
That helps.
Well, okay, when I disclose the grading scheme, it's actually better than a video clip, because I explain on which line of the original program it should be fixed on which line of the solution and how it should be fixed.
Because the issue with this exam was the time. For me, it was the time. I just want to know how you approach the problem and how you just
But that's kind of unfair because I started off with a solution and I just went back and demolish it, right? So it's a little bit different. What I can do within that amount of time, may not be comparable to what you guys can do. But the thing about the exam 2 is it was by design from the get go to have partial credit. But originally I was giving partial credit, depending on how many test cases work for each subroutine. But since most people did not come close to getting any subroutine to work, I had to adjust the grading mechanism to actually look for things that needs to be fixed and look for those fixes in your programs, and then assign the grades or assign points accordingly. Now that will work in a class like this, but it will never work at work. But boss, I fixed 75% of this program. But it's still not working, right? No, when you're working, it depends on the company. Some companies are fairly relaxed, and it depends on what project you're working on. For instance, if you're working for, let's say, Pixar, okay, and the movie already has a release date, and the software has a bug, then how fast the team can get it fixed, that's not negotiable. That is not negotiable. Yep.
When your application is due in 2 hours, and you've just spent the last 2 weeks fixing it, and you haven't pushed your Git repository upstream yet, and your workstation hard drive crashes, you've got 2 hours to reconstruct it from the old broken code.
No, you have 2 hours to run away from the company as far as you can. Yes. Yeah, I would use those 2 hours to try to drive away, especially when you work for a shady company. Okay, so I don't think you guys have too much to worry about the test. Okay, after adjustment, everything is good. Okay, so what we'll do today is 2 things. One is I have to give you guys a homework assignment, which basically you have to write a subroutine in assembly that is sandwiched between a C subroutine and another C subroutine. So I would have a C subroutine, namely main, to call your subroutine, and then your subroutine will have to in return call, and utilize another subroutine. So this is a good practice, because from the perspective of your subroutine, you will have to understand, how parameters are passed to you. But at the same time, you also have to set up the stack to pass the parameters to yet another C subroutine. It's a good test to see whether your program, plays by the rules. So that's something that we'll do today, is to have an assignment like that. It is not assigned yet, and I do not want to use the assignment from last year. So we're going to do something different this time.
Are you going to give an example?
Easier? Well, I don't know. With the
testing
average
gonna be
of the second exam being 60%, I think it doesn't have to be easy. I mean, 60% for an average is actually pretty good
No.
in my classes. Yes, it is.
His grading scale, that's a B. That's almost a B.
Yeah, exactly. That's exactly my point.
That-
A B is good.
Yeah.
A is excellent, B is good, C is satisfactory, D
Yeah,
is
yeah,
pass,
right.
and F is fail.
Just to Davis with straight C's. You're not satisfactory.
All right.
B is average, B is below, C is complete failure.
It depends on how you look at things, yes.
Anything less than perfection is failure.
Well, I wouldn't say that either. Okay, so we were talking about structures, and we're almost done with structures, except we haven't done this part yet. In other words, we have not talked about how to return a structure in C and how to do it in assembly. Okay, so let's go ahead and take a look at this code here. This is plain C. This is not C++. Okay, I'm not even using anything from C++. This code will compile using a plain C compiler. It does not require C++. So once again, I use struct to define the structure. In this case, the template or the class, quote unquote class, is called X. It has two members. One is called P, and the one is called Q. Okay, never mind. Okay, and I have a subroutine here, called makeX, and what it does is it will take two parameters, I and J, and the parameters are very easy, because all I do is to have a local variable X, which also has, which is also of struct X type. I initialize that so that P gets the value of I and Q gets the value of J, and this is the interesting part, because I am returning my local variable V, because over here I specify that this particular subroutine can return a structure. Okay? Are there any questions about the subroutine itself? Okay? So what we can do is, in the main subroutine, I can now do something like this. In the main subroutine, I can define my own local variable W, and then I can say W equals makeX 2310, which are the parameters that I pass to the subroutine. Have you guys learned anything like this from your C class?
Yeah, that's how you catch it. That's how you catch the return value.
This is how you utilize the return value, yes. Because the return value is just a struct X thing, and one of the things you can do with it is to copy it to the variable W. Yep.
That's really bad code. You should be creating a pointer to a structure, passing that pointer to the function, and by reference, and
but then I won't be illustrating how to return a structure.
True.
So the whole point is to illustrate how to return a structure. Okay, so what are we going to do with this one? Now, the first thing is you have to focus on the invocation, which is this part here. Because the actual return value is more important to the caller than the parameters, it is pushed first. So from the caller's perspective, this is what we do first. We are subtracting the size of X from the stack pointer. Now this is of course assuming X underscore size and all the other things related to X are predefined already. But we already know how to define those items. Do you guys still remember from last time?
Yeah,
That's like 2 weeks ago. Yeah.
C program to print labels.
Yep, a C program that has a bunch of printfs so that I can print the offsets from the beginning of a structure to the beginning of each member inside the structure. So this line reserves the space, and then what we do is we move ESP to EAX because I need to save that value. I cannot push it right away. That's the last thing I have to push. Then I will push the parameters. Okay, 10 and 23 are the two parameters. Basically 10 is the second parameter and 23 is the first parameter. And this is the implied parameter that is pushed. It is the address of the space that I have reserved for the return value. In other words, it is almost as if I have 3 parameters for this subroutine, because the address to the return space is actually quote unquote one of the parameters. But you don't see that when you look at the C code, it is just implied. Are there any questions about this? No questions? And then from inside the subroutine, inside make, this is how I would look at the frame. Old EBP is still pointing to itself, and therefore the displacement of the saved EBP is 0 from where EBP points to. The return address is still right on top of that. This is new. The return value address is right after the return address itself. Okay? Does everybody understand the differences between a return value address as opposed to the return address? The return address is what we use for the return. The return value address is just the address of this space that we reserved earlier. Is that doing okay so far? And then we have the two parameters. We have the first parameter, then we have the second parameter. And this part here, v equals old EBP minus x underscore size, that's just for reserving the space for the local variable. Because I do have a local variable in the C code. Now in assembly, I really don't have to do that, because in assembly, I can directly access the space that is reserved for the return value. But since I want to replicate exactly the same mechanism in the C code, this is what I'm doing. I have a local variable just like in the C code. Are we doing okay so far with this code? Sort of. Do we know what is happening to the stack? We first reserved a chunk of space for the return value, then we push the parameters, then we push the address of the space that we just reserved. Then we make the call. Inside the subroutine, we do exactly the same thing as always. Basically, inside the subroutine, we have not that part here. Inside the subroutine, we still have to push EBP first, move ESP to EBP, and then we reserve the space for the local variable. Is that okay so far? Sort of. Okay, I'm going to write the subroutine next. This is the code from the caller's perspective. The return statement translates to copy v to whatever the return value pointer points to. So in other words, if I want to translate this part here, just this line, come on, highlight. If I want to translate just this one line in the original C code, it will become this particular subroutine. Well, let's find out what this one does. I'm going to use memcopy. In other words, I'm not writing my own loop to copy x underscore size many bytes. Does everybody know how to use memcopy? No? Okay. This is a low-level thing, so it is not surprising that they do not talk about that in the C class. So what you want to do is to memcopy, CPY. And it explains, memcopy is a very simple subroutine. It does one thing. It just copies a block of bytes from one location to another location. And you get to specify the source, the destination, and the number of bytes to copy. It's really as simple as that. The parameters that it takes, is the first parameter is destination. It is a void pointer, which basically just specifies a location. Where am I supposed to copy that stuff to? The second parameter is a source, which is a const void pointer, which is basically specifying where do I copy from. And the third parameter is the size, which is the number of bytes I'm supposed to copy. That's how you use memcopy. Are there any questions about memcopy itself? Okay, you specify the source, you specify the destination, you specify how many bytes to copy, you call memcopy, and it will get it done. Okay, so switching back to the notes here, this is the return statement. So what the return statement is doing is it's setting up the parameters to call memcopy. The first part it has to set up is to specify the number of bytes to copy. Because remember, we have to push the last parameter first. And that's what it's pushing, is the number of bytes that we are copying. The next one is the source. Where are we copying from? Now, where exactly are we copying from? We are copying from the local variable v. So that means we have to do the calculation and push the address of local variable v. This is one way to do it. We push EBP first on the stack. So now the stack pointer is pointing to the frame, a copy of the frame pointer. Then we add the displacement to the local variable v to whatever I just pushed on the stack. And that turns out to be what? What did I just push on the stack? The frame pointer. So frame pointer plus the displacement to local variable v becomes what? The address of local variable v. So we end up with the address of local variable v on the stack after these two instructions. Are we doing okay so far? Kind of? Okay. Then we will push the third item on the stack. The third item is the first parameter to mem copy, which is the destination. Where are we copying it to? This, this does not require the calculation of the address because what I see on the stack is the address. This is the implied parameter when we invoke the subroutine makex. So we call mem copy to actually perform the copying. When mem copy comes back, we have to deallocate the 12 bytes that we just allocated for the 3 parameters, each one taking up 4 bytes, and then this is all done. This is the return statement. Are we kind of doing okay with this? Do you guys want to see an example? Yep.
So, the basic pointer points to the return address.
The frame pointer?
Yeah, the frame pointer. Well,
The frame pointer points.
I don't understand why you pushed the EBP.
Yeah, couldn't you have just pushed EBP plus V basically?
If I could do that, that's what I wanted to do, but I cannot do that. Are you talking about V, open paren, EBP, close paren?
Yeah, like what you did with.
But that won't do it, because this is pushing. Okay, let's not deal with the push L instruction here. Just focus on the operand. Okay, what is this operand saying? This operand is saying I'm going to push 4 bytes. Okay, because of the L here, so it's going to access 4 bytes. It's a memory operand. Okay, what is the effective address of the 4 bytes that I'm copying?
The value of val address plus EBP.
The label value of return value address, and the value of EBP at the time when I execute this instruction. That becomes the effective address. Then I will go to that location, grab 4 bytes from that location, and push those 4 bytes on the stack. That's what this push L instruction is going to do. But that's not what I want to do with V, because V is not an address to a struct X. It is a struct X. So I don't want to just push the first 4 bytes of a struct X on the stack. I want to get the address of that struct X and push the address on the stack. So that's why the treatment is a little bit different between V versus return value address. Okay. So are we kind of doing okay with this? Yep.
Possible to turn off the lights, so that's
To improve the contrast. Like that. Is that better?
Yeah, much.
I think the lamp is probably dying because I think it was a little bit better than this before at the beginning of the semester. Was it kind of better?
Wouldn't remember to know.
There's no comparison, right? All right, so let's go ahead and write some programs. Write a sample program to illustrate, all the things that we just talked about. And I will do that in today's folder. That means, it is kind of important to study the sample code in these folders, because it contains, not only the sample programs, but also, the entire program that we do in the class. Okay, so we'll go ahead and make something that is relatively simple to do. Now, because of the lack of time, I'm not going to go through the exercise of last time. In other words, I will just make assumptions about, the structure what is the address of each member of a structure compared to the beginning. Because most of the time you can actually just imply that, because that's not the focus of this exercise at this point anyway. So I'll go ahead and write the C portion first. Okay. So the C portion will define a structure. Let's define a structure called what do you want? Okay, let's say complex. Okay. So we are dealing with a complex number, but we can only use integers for both the real part and the imaginary part. That. Okay. And we want to create a subroutine. Okay. This part is commented out because that's the subroutine that I want to write. And we can do it like this: struct complex. It is going to return a struct complex from the subroutine. Do you guys want it to be easy or a little bit more difficult?
Surprise us.
Make it as hard as you can so that we can always do the easier stuff from it.
Let's do an add then. Okay, so we'll do an add, and it will pass a pointer to a complex number first, PC1, and it will pass. It will pass another parameter which is also a pointer to another complex number. Is that okay so far? Inside I will have a struct complex as my return value. Okay. So X gets what? PC1 points to R, X dot R. This is a good example, because it illustrates a few things that we have talked about already, and this is the first time we actually see how to do it. X dot I gets PC1 points to I plus PC2 points to I, return X. Is that okay so far? That's the subroutine I want to implement. Okay, now we have the main subroutine. In the main subroutine, I can define one struct complex, and let's make it 0. Like that. And let's see. I'll use another one for the result. Result. That. So the only thing I will do in the main subroutine is result gets add the address of 0, the address of 0. Okay. The actual calculation is irrelevant. Okay, that's not the main point of this particular sample program. You guys can always change the program a little bit later, to make it more interesting. Because assuming the subroutine is done correctly, it should work regardless of what value you pass to it. Okay, are we doing okay so far here? Now, if you want to make it more interesting, you can just have some kind of dummy instructions here. Let's see, what would be a good dummy instruction? 0 dot I gets 0. Okay, that is completely redundant because it is already initialized to 0. But this gives me a chance of stopping the program right after this line so that I can examine the result to see whether it worked or not. Okay. Are there any questions so far? Okay. All right. So now I have to go ahead and actually write this particular subroutine, but in assembly, not in C. This is line 8 to line 15. So I turn it into comments. Now in this case, because the complex number X, the complex struct complex is relatively easy, I'm just going to make assumptions instead of making another C program to print out the displacements into the individual members. I'll just make assumptions. So in general, you should not do that. Okay, in general, you should always rely on the C program to print out the displacement to each individual member inside the structure, because sometimes your assumption works, but other times it may not work. Sometimes it works depending on the options that you supply to the compiler. If you tell the compiler to make your structures more packed, sometimes it will rearrange things a little bit, and your assumptions will not work anymore. Okay, so I'm doing this only because we are short on time, and two, in this case, it's fairly predictable. So to do that, I just have to define complex underscore r, which is the real component of a complex number, to be 0 because it is the first member of the structure, and therefore it is 0 bytes away from the beginning of the structure itself. Is that okay so far? Okay. And then complex underscore I is going to be 4 because R itself is taking up 4 bytes. Now this is also making a very bold assumption. I'm assuming an integer is 32-bit. Depending on your compiler, int can be 16-bit, can be 32-bit, can also be 64-bit. So this is definitely a dangerous assumption. But since I kind of know this tool chain, so this is what I can do as an assumption. I would also define another variable called complex underscore size, which is the size of a struct complex in number of bytes. So that will be 8 bytes. Are we doing okay so far about these 3 symbol definitions? Is that okay? Okay. And now we can go ahead and try to write the subroutine. Now to write the subroutine, the first thing we have to do is to figure out how to where things are on the stack. So we'll go ahead and define the displacement of individual items on the stack, starting with old EBP. That's always 0. And then we have the return address is old EBP plus 4. And this time, because it is returning a structure, like here, I also have to reserve, it has a return value address in this case, which is right after return address. Then we have the 2 parameters. We have PC1 being right after return value address, and then we have PC2 right after that. Are we doing okay so far with the symbol definitions? These are almost identical to the example that I have in the notes. And then here, because I have a local variable x, we also have to reserve space for the local variable x. So we say x equals old EBP minus the size of a struct complex, because that's the number of bytes I have to reserve for x. Are we doing okay so far with the definitions of the symbols? Each one represents a displacement from where EBP points to that particular item. So now we can go ahead and actually write the program. When you write a subroutine, especially one that has local variables and parameters and stuff like that, we always follow the same structure. The first thing we do is to push EBP, and then we copy ESP to EBP. When you exit, it's exactly the opposite. So you have to move EBP to ESP, and then pop EBP from the stack, and then do a return. Are we doing okay so far with the epilogue, which is what you do? The epilogue is what you do after, and then the prologue. Is it the other way around? Yes. Prologue is what you do after, and epilogue is what you do before. So are we doing okay with those 2 pieces? No?
Yeah, we're doing okay, but now prologue is before.
Oh, prologue is before, and then epilogue is after. Excuse me.
You had it right the first time.
Yep. Okay, now we have to reserve space for the local variable x. To reserve space for the local variable x, all you have to do is to add $x to ESP. Is that making any sense? At first glance, it does not make sense, because how come I'm adding a value to ESP when I'm supposed to be reserving space? But when x is negative, exactly. I do not need anything at the end to deallocate those bytes, because when you copy the frame pointer back into the stack pointer, everything is restored. So there's no need to explicitly deallocate space that we reserve for the local variable. Are we doing okay so far? Okay, so now we have to move on and deal with the addition. We are adding the R member of what PC1 points to the R member of what PC2 points to. Then we'll copy that result to the R member of the local variable X. Okay, how am I going to do this? Just focus on PC1 points to R. How are we going to do that? Well, let me ask you what this is. Okay, if I say move L PC1 EBP using the based addressing mode and put it into EAX, what is EAX at this point? If I want to write the comment right next to this line, how should I comment what is EAX?
PC1.
It is PC1, so in terms of types in C, what is it? Is it a struct complex? Or is it a pointer to a struct complex? It's a pointer to a struct complex, okay? So we'll comment here and say EAX is a pointer to a struct complex, okay? Now that is important because if EAX is only a pointer to a struct complex and I want to access the R component or the R member of that, what do we do with
Dereference it?
We have the dereference, but which addressing mode is the most handy to access just the R member of that structure? The based addressing mode again. Okay. So what I'll do is I'm just going to push it on the stack. I'll do the calculations on the stack. So I will push R. Oops, you take it back. It's complex underscore R, which is the displacement of member R from the beginning of the structure. And I would use the base addressing mode because EAX actually points to the base or the first byte of the structure. Is that making any sense? Okay, so let me comment here. Push the R member on the stack. Is that okay so far? Yep.
Pretty much what you're doing is you're just grabbing it from the structure and just pushing it back into the stack so you have access to it.
Well, so I can use it later. Okay, I'm just pushing it on the stack, but I have plans to use it later. Okay, I can do the same thing with PC2. Okay, PC2 EBP to EAX. I can use another register, just to be handy. I can use another register for that purpose. Okay, and I can either push it on the stack, or I can just move this one to another register. Let's say ECX. So this time I will move complex R EBX to ECX. So it's
You're
kind of,
missing I.
oh, you're right. Okay, so EBX is a pointer to. It should be I. Oh, it should be R because it's the same R component for both. Sorry. Okay, so the third instruction is to basically say ECX is PC2 points to R. Are we doing okay so far with this? Okay, so now I want to pop back whatever it was on the stack and add it to ECX. There are several ways to do it. I can pop it into a register and then add the register to ECX, or I can do something like this. Okay, I can add whatever the stack pointer is pointing to and just add that to ECX, and then I can deallocate those 4 bytes. So this way I don't have to use one other register just for that purpose. Yep. Yeah, I suppose we can do that. No, because I just do whatever came to my mind first. That came to my mind first. So this is the other way to do it. Probably is a more direct way to do it, because then you can just add. That's more direct. Thank you. Yep. Oh, the comment is wrong. Yes. Is PC1. How's that? We still have one more thing to do. We have to store that back to my local variable x. I can do it with one single instruction. Can someone tell me what I should do here? Okay, since we're copying, we know that we have to use move L. We already know the result is in ECX, but where am I copying it to?
X displaced by R. There you go.
Something like that?
Yeah.
So the question is that okay? I mean, can I mix these two on the same line? Can I say x plus complex R and then have the whole thing to become the displacement of a based operand? Yeah, we can. Because in this case, remember what x is. What is x? X is the displacement from where EBP points to the first byte of the local variable x. That's what x is. What is complex underscore R?
The displacement to R.
It's displacement from the base of a complex structure to the member that we call R. So it's perfectly okay to add these two components together because they're both displacements, and we're dealing with not what x points to, because x itself is a complex. It's a struct complex. Yeah.
So the base is always 4 bytes. It automatically assumes that.
The base.
Never mind.
Okay.
Yeah.
So that takes care of the first instruction. To take care of the second line of C code, we can just copy and paste it and change R to I. So we have 5 lines here. 5. Copy over here. And then we can say substitute. I have to be careful about the R because
You know.
hmm?
You don't have to be careful.
There are no other occurrences of R?
Only in your comments.
There you go. That worked.
You have pointies.
Huh?
It's dukes.
Yeah, Ponte.
And struct. Duke.
There we go. Okay, so, but these two are relatively easy. Okay, now that we understand how to get to a pointer or where is the pointer pointing to, this is my big problem now. How do I return X? Just copy and paste what we just talked about, right? Use memcopy. Now, how do we use memcopy again? What are the 3 parameters, starting from the last one?
The size of whatever your
How many bytes to copy? Okay, in this case, it will be complex underscore size, but it has to have a $sign in front. Okay, because we are specifying this many bytes and not go to that location to grab the 4 bytes. That's the easy part. And what is the second operand? I mean, the second parameter, source. And the source in this case is what? Is it local variable x or the address of local variable x? The address of local variable x. What is this going to do? It will do something. It won't crash, but it's not the right thing to do because what is this going to push on the stack? It's copying the first 4 bytes of x on the stack.
just pushing R on the stack.
It's basically pushing R on the stack, yes. Effectively, it's pushing R on the stack. But memcopy is going to use it as an address, and it will just fail. So we cannot do something like this. Instead of doing this, we'll do the same thing as in the notes. We'll push EBP on the stack first, and then we'll just go ahead and add the displacement back onto the stack. So in this case, we're adding $x, which is the displacement to local variable x from where EBP points to the item that we just pushed on the stack. What is the first parameter?
The destination.
The destination. And in this case, where is my destination?
Return val address.
return val address, but that's just a displacement from where EPP points to. So you have to make sure that you use it in the context of a based operand, like that. Then we can call memcopy. When the memcopy returns, technically speaking, I don't really need to clean up the stack at this point because I'm going to not only clean up these 12 bytes, but also the 8 bytes for my local variables by just copying the frame pointer into the stack pointer. But it is always good practice just to clean it up, just in case we need to add more code right after the memcopy. So we'll just go ahead and do that, which is add along 12 to ESP. But this instruction is not needed. Are we doing okay so far from the perspective of the subroutine that we're calling? Is that good? Not good? Kind of good. Well, let's see whether this works or not. Okay, so that brings us to a Makefile, because in this case, well, you don't really need a Makefile, because if you want to recompile everything every single time, you can always do GCC-O, and you have to name the output file, which I just call main here. Then you can supply all the source code file, all the source code file in this case. It's not going to work because I forgot one thing. I forgot to do a .global add. Okay, because if I did not do this, then add is a symbol that is defined only within this object file. The linker would not be able to see the label add.
Yeah.
And I have not even defined that yet. Okay, so there we go.
Now it's ready.
Now it's good. So GCC-G to specify we want debug information, -O to specify the name of the output file, which is the executable, and then we just have to supply the source file names. That incompatible types when assigning to struct from typed int. Okay, line 23 of main. Oh, I need a prototype. Because as far as the C compiler is concerned, it does not know what add is. So I have to tell the C compiler, even though it is not written in C, this is how you talk to add. Is that okay? That's just a prototype of the subroutine.
Yeah, you need to see if you pre-declare it.
Do it again, and it's all working. So now we can do a GDB. Put a breakpoint on line 25. Now, how many people think this program is going to crash?
I don't trust that.
Yeah, me neither. Run. Ah, it did not crash. Let's go out. Let's go and find out what was zero. Print 0. 0 is 0, 0, which is good. But that's okay because no matter how many times I add 0 to 0, it is still 0, right? So to test this program in a better way, I should probably change main.c so that 0 is not exactly 0. Okay, or better yet, make them different.
Make them different.
Make them different. Print 0. Of course, this is a bad variable name at this point because 0 is not really 0.
Well, it depends what coordinate system you're in.
Well, it did not get the job done, did it?
You're not printing result.
Hmm?
You're printing 0.
Oh, that's right. Duh. Okay. So it worked.
I was wondering why you print 0 the first time, too.
Okay, so this is one way to do it. Now, the opposite way is to write the subroutine in C, and then you make the call from assembly code. Okay? So that's what we want to do too, is to see whether we can do it from the opposite way. Because at this point, I have only illustrated how to return a structure from inside the assembly program. But I also need to show you how to set up the stack so that you, writing an assembly program, can call a C subroutine that returns a structure. So we have to kind of demonstrate the opposite way. Well, we can use the same program. We just have to change the program a little bit to make that work. So what we need to do is to uncomment add. So, sorry?
Can you like make another file?
Can you copy?
Too late.
So that you can compare.
Okay, all right, fine.
Please. Check it in.
There we go. All right, so this time we're going to write the subroutine in C, and the other subroutine, which I will rename as stub, is what I will write in assembly. Stub. Like that. And the main program is just going to call stub. Like that. Okay? So this time...
You better make that void stub.
Oh, right. Because otherwise the C compiler does not like it.
Well, you're giving it a return type of, you're just calling it out anyway. Yeah, there we go.
There we go. Otherwise it would complain, just complain. Okay, so this is what we'll do this time. This time around, we will go ahead and write the we'll implement stuff in assembly. And when we do it in assembly, we don't need that line. Okay, so we have line 16 to line 22. 16 to 22, copy, paste. Dot global stub. And this is the beginning of stub. Stub is easier, but it's not like super duper easy, because I still have to define the structure of X. Well, I don't exactly need to define everything. It's kind of handy to do that. So I'll just go ahead and define some of that stuff. This is probably all I need to access a complex, or this is the only part that I need about complex for this program. Okay. So we'll go ahead and write define the other symbols. Old EBP is 0. Return address is old EBP plus 4. I have no parameters, so that's the end of one side of the frame pointer. The opposite side of the frame pointer has two local variables. So we have 0 here, and 0 in this case is old EBP minus complex size. And then we have the other, we have result. Result is 0 minus complex size. Are we doing okay so far? Okay. Now in this case, the ordering or the address of 0 and result is probably opposite to their equivalent addresses when you write it in C. When you write this program in C, most of the time 0 has a lower address than result. But the way I do it is that 0 would have a higher address than result. It's not a big deal because we don't need to rely on the ordering of the addresses of local variables. So it's not a big deal. It's just something that you should kind of look at. You should look at this and kind of understand the ordering of the local variables. So now we go ahead and implement the subroutine. Push L EBP and copy ESP to EBP. When we get out, we have to do the exact opposite. So we copy EBP to ESP, pop L EBP, and then do a return. Okay. Now I have to reserve space for 0 and also to get it initialized at the same time. How should I do that? What about this?
Good enough.
That would do it, wouldn't it? Okay, because it's going to reserve 4 bytes first and initialize, the second member of 0 to 2. Then we'll push the 1, which is basically the same thing as initializing the first member of 0 to 1. Okay, so it's a tricky thing to do, but you can do something like that. But if I do it this way, and I have to reserve the space for the other variable, pretty much the same way, I can no longer add result to ESP, because that will just mess up everything. Well, it's going to reserve more bytes than I need, and that's not something I want to do. So we'll just go ahead and add L or subl. Technically speaking, the best way to do it is to add L, and this time, I have to use 0 minus result, or the other way. I think it's result minus 0 because I have already allocated for local variable 0, so there's no need to allocate for that much space anymore. I'm just allocating for the remaining portion of my local variables. Is that okay so far? When you look at the definition of result, what exactly is it? It's -8. What is the definition of 0? It's -4. What is -8 minus -4? It's -4.
I think it's -8.
-8.
Sorry?
Complex size is 8. 0 minus 8 is -8. -8 minus 8 is -16. 0 is -8.
0 is no. 0 is -4, and result is -8.
Old EBP is 0. Complex size is 8. 0 minus 8 is -8.
The very first line.
The very first line.
Complex size is 8.
Oh, okay, 16 versus 8. Sorry.
Yeah.
Yep, you're right. Okay. But the calculation is still right. I just forgot that each item has 8 bytes instead of 4 bytes. But that's a good thing because if I had used the actual numbers, then I would have allocated the wrong number of bytes. Symbolic constants is the way to go. I just made a mistake. If I had used literal constants, I would not been able to catch it, and actually have put the error into the code. Okay. Now we have to implement this particular part, which is a single line in C. How do we do this one single line in C, but do it in assembly? First of all, what do? We reserve, first of all, we reserve the space for the return value, okay? So we'll just write a comment here and say reserve space for the return value.
We also have to put the parameters on the stack.
Sorry?
We also have to put the parameters on the stack.
But not before this. I have to do this part before we put the parameters on the stack.
Oh, I thought we were making all this.
No, you have to do it exactly this way. So this time I have to use subtract, and we are subtracting the size of a complex from the stack pointer. We're reserving 8 bytes on the stack. Then I'm going to copy ESP to EAX because I have uses. I need to take a snapshot of ESP because I have to push EAX later on. If I don't save it now, ESP is going to be modified by the additional pushes, so that's why I need to do something like this first. What do I do next? I have to pass the parameters, the %0. How do I pass %0 on the stack? I'm passing the address of my local variable 0 on the stack. Haven't we done something like that before?
Yeah, you push EBP plus 0.
That'll do it. Right?
This one pushes a value, this one pushes an address.
And then we have the other one, which is also 0 itself. Push it twice on the stack. Then we can call, oh, there's one more thing to push on the stack. What is it? It's the address of the return value. Okay, so that will be in EAX. So just push L, EAX. Haven't we seen something like this before? It's in the notes. It's almost exactly the same. It's not exactly the same, but it is very similar to the code that is already in the notes. So at this point, we are ready to call the subroutine. So we are ready to call, what is it again? Add. And when we return, we have to utilize it. Okay, what are we going to do? Sorry?
No.
How are we going to utilize the result? We have to store the return value into my local variable result.
So move the map copy space thing.
We're going to use mem copy again. How many bytes are we copying? Well, first of all, let's clean up the stack. How many bytes have we pushed on the stack just for the parameters?
6.
No. We cannot deallocate everything just yet. Okay, we can only deallocate everything except the return value itself.
Oh,
We have 4 bytes for the first pointer, 4 bytes for the second pointer, and 4 bytes for the pointer to the return value. So we have 12 bytes that we can free at this point. Is that okay? Does everybody understand why I can
Don't you
only
have to keep the pointer to the return value so that you have access to the return value?
Well, let's think about it. Okay, what do you think the stack pointer points to right after these instructions?
It points to.
It points to the return value itself. Okay, let's draw a picture. Okay, let's draw a picture using a text file. Okay, so what we have here is the first thing we did was we reserved the space for the return value. Okay, so we have return value dot, let's see, I is the second component, return value dot R is the first component. That's the first thing that we push on the stack. Then what do we push? Then we pushed, the %0. Then we pushed %0. Then we pushed ampersand return value. That's what we push on the stack right before the call instruction. Is that making any sense?
Yeah.
So if I just deallocate these 3 items, 12 bytes on the stack, then the stack pointer will point back to the return value itself. So I did not lose, the location of the return value. In fact, the stack pointer points right to it by the time I get back to this point. Okay. But I cannot, I have to change the stack pointer right away because I have to push the number of bytes to copy. So there are several ways to deal with this. You can always just kind of manually keep track of, how many bytes this is taking. Then you can push the stack pointer itself on the stack and then just make a little adjustment to it. Because the stack pointer, when you push it on the stack right now, is going to be 4 bytes lower than what it is supposed to point to. So now you have to add 4 back to whatever the stack pointer points to. Does everybody understand why I have these 2 instructions? When I push ESP, it is too late already, because the stack pointer that I want is before the first push instruction. To get back to that location, I have to add 4 to the stack to whatever the stack pointer points to, because that's the old stack pointer before this push instruction. Kind of convoluted? Too convoluted? Okay, let's make it not so convoluted. How about we just take a snapshot of stack pointer to EAX? Then we don't have to go through all that complicated stuff. Is that making any sense? Is that better? Is that better? Okay. There's one more thing to push, the destination. Where is my destination?
Result. So you
Result.
press result.
This time I do have to go through this kind of calculation. Because I'm pushing the address of result, not the first byte of result on the stack. Yep.
Why can't you? Never mind. I just answered my question.
Oh, okay. So I'm adding 12 to the stack pointer to deallocate the result of the mem copy. And there's one more thing to do. What is left on the stack at this point? I don't really officially have to deallocate it. I want to find out what is on the stack at this point, right after the add 12 to ESP.
You have the return value at 0.
The return value is still on the stack. So technically speaking, you should deallocate that as well, which is basically adding complex underscore size to ESP. But since addition can be combined, I can just say add 12 plus complex size, because I can combine the two adds into one. And technically speaking, I don't even need this, because the next instruction is going to restore the stack pointer back to where it was way before, back to where it was before I allocate for the local variables.
No, you have 0 left.
You
have 0 left after that.
I have 0 left. What do you mean?
When that gets rid of result, you have 0 remaining. The variable 0.
The variable 0 dot.
The structure 0.
Yes, I have struct 0 and struct result both on the stack.
And that gets rid of result, you still have 0 left after that instruction.
No, this does not get rid of result. This gets rid of the return value, the space that are reserved for the return value itself.
Yeah.
So both local variables are still on the stack at this point. Okay. All right. So let's see if this works or not. So we want to do a gcc-g-o main.c stub.s. Whoa, it compiled the first time. That's not usual. That's not common.
Sign. Bad sign.
Bad sign.
That just means you got a logic error.
Very good. That's probably what it is. So what we want to do is to put a breakpoint into stub, because the interesting part of this program is in stub. If I put a breakpoint outside of stub, I won't be able to see anything. So let's go ahead and look at what stub has. Okay. Do we want to stop it early or do we want to stop it late?
Early.
Early? Yeah, don't trust me. Huh? Okay, let's put a breakpoint at the first instruction. So just B stop will do it. So this will stop at the very beginning of the stub subroutine on the very first instruction. So we run it. We are now at the first instruction. Nope, it's not the first instruction, is it? That's interesting. It executed the first 2 instructions already. Okay. Single step, single step. Okay. So at this point, I have allocated space for both local variables, both result and 0. 0 should also be initialized at this point. How do I look at that? How can I verify that local variable 0 is in fact initialized so that the first member is a 1 and the second member is a 2? Examine 2 things. Each thing is a word, because a word in a debugger is 32-bit. I want to display that, well, decimal is fine because it's just 1 and 2. How do I specify the address? EBP minus or plus typecast the address of 0.
I was just thinking that.
Okay, let's take a look at why we have to go through all this convoluted stuff just to take a look at the content of the structure that we call 0. EBP is fine because we know everything is on the call frame, and EBP is a stationary point, so that's why we use EBP as an anchor, or where EBP points to is an anchor to access everything else. We know that 0 is defined as a label, but as a label, it is defined to be what? Negative
8.
Negative 8. But if I don't do the typecasting, it will try to treat negative 8 as an address. and then go to that address to grab 4 bytes to add to EBP. That's not my intention. That's not what I want to do. So what I need to do is to say, no, it is not, 0 itself is not a variable. It is, just treat it as, take the address of that, so do not do any dereferencing. When you put an ampersand before a symbol name, it simply tells the debugger, do not dereference. Okay? Just use whatever value the label is, in this case, as an integer. Because if I don't cast it to an integer, then you're adding EBP to the pointer to an integer, so that would be like totally wrong too. It would get you to the wrong part of the memory space. Yep.
What does it do if you don't do that?
If I don't do the int,
Yeah.
you mean something like this?
Yeah.
Okay, well, let's find out what the debugger will do. The debugger will look at this and it will say, okay, EBP is a void pointer, so you can do anything you want with it. But the second part is a pointer to an integer. So what happens when you add, a value to the address of a pointer, to the address of an integer? It will multiply whatever EBP has by 4 and then add it to the quote-unquote address of 0. So this will probably end up with accessing a location that I cannot access. Argument to arithmetic operation, not a number or a Boolean.
It's not even a number.
Because they are both addresses. It looks at EBP as a pointer already, and then the address of 0 is also a pointer. You cannot add 2 pointers when then. Well, in this case, you just plain cannot add 2 pointers. You can subtract pointers, but you cannot add pointers. You can subtract pointers to find out how many elements are between the 2 items, but you cannot add 2 pointers because it just does not make any sense. Okay, very good. So we know that the stack is properly initialized at this point, and we'll go through the single stepping here. We are calling add at this point. I want to see if I can skip over this. What is the command to skip over, a subroutine call?
You just want to skip the line.
Step until it reaches a different line.
Just step to line 35.
There's a particular command to step over a subroutine call, so it doesn't go into the
Help
subroutine.
over? Try help over.
Help. And in this case, it will be
Apropos over.
sorry.
Apropos over.
Help what?
No, apropos. APRPOS.
APRPOS.
Over.
APR.
POS.
That doesn't
Space.
sound right.
PROPOS.
It's APROPOS.
Okay.
Space over. Set the mode of the step operation.
Set step mode. No, there's another command to do it. Just cannot remember what it is.
Can you just add 40 instruction pointer? Add 40 instruction pointer?
What I can do is to find out where I am at this point and then just, put a breakpoint on line 35. I just cheated. Right? I mean, if you wanted to skip over, you just put a breakpoint after the call and then, just continue execution. Okay, so pretty much, just housekeeping stuff. Now I'm going to call memcopy. I probably don't want to track it down, so I will do the same thing here. Put a breakpoint on line 42, and then just continue execution. Oh, just stepped way too much. That's okay. Nothing has happened to the stack, so the result should still be on the stack. I just have to figure out how to get back to it. Okay? I have already popped EBP, so my original EBP is gone already.
So your stack pointer's right.
I still have my stack pointer. Now, how does the stack pointer relate to the frame pointer in this case?
There.
Now, remember, this is after the pop instruction.
There's
Be
4
identical.
above stack the frame pointer.
Exactly. So if I look at the stack pointer, this is pointing to 4 bytes above what EBP should be pointing to. So I want to examine 2 things. Each one is a word with ESP plus 4. ESP minus 4. Okay, ESP minus 4 is my EBP. Okay, so I just have to do the rest of the calculation from here. And typecast result. That should do it. Nope.
I guess it doesn't like the 4.
No, it likes the 4 just fine. It just is. Okay, let's see.
That's no way
So that works. ESP minus 4 worked. Sorry?
I was looking at the line above it. The 77 FC, there's no way that would
This is before I execute the return statement. So the stack pointer is pointing to the return address. And 4 bytes below the return address is what the frame pointer used to point to. So this really should be correct.
Try without the ampersand.
No, that definitely won't work. And it works the same way. That's interesting. Well, what is supposed to be result? Is it 16? Negative 16?
Yeah.
That's not correct.
It's supposed to be 2 and 4.
It's supposed to be 2 and 4. And now it is 4 and 4.
The way you just rerun it with a breakpoint at the right line.
All right, let's do that.
That's too easy.
42. Go.
No, because if there's a problem, I want to find out where the problem is.
So just
So-
rerun it. All your breakpoints are the same.
Hmm?
If you just rerun it, all your breakpoints are the same.
I want to put a breakpoint. I want to put a breakpoint right after add because I want to look at the return value on the stack to see whether that part is set up correctly. So let's put a breakpoint on line 35, which I have done already. So start from the beginning. Continue. Okay, so what is on the stack right now? This is right after the call instruction. There are a whole bunch of items on the stack right now. There's okay, let's take a look. Examine probably a whole bunch of items on the stack. Let's say 1, 2, 3, 4, 5. 5 should do it. 5W in hexadecimal. And we want to start with where ESP points to. This is the stack pointer. Okay. So the calculation was done correctly.
There's 2 and 4.
No, this is not right.
I think it's mad that we skipped over add.
The stack content is not right because this is before I clean up the stack, before the adding of the 12 bytes here. I think I forgot to push one more thing on the stack because this is supposed to be the address to the return value. That was not pushed. So this push instruction was not pushing the right thing on the stack.
Well, you pushed EAX instead of EBP. Oh no, EAX is right. It was storing ESP at the time.
Okay, let's check it again. Okay, this instruction reserved the space on the stack for the return value. We save it into EAX, and then we push the address of 0 on the stack. We push the zero. We push the address of 0 on the stack, and then we push the return value, the address of the return value on the stack. So that seems correct to me. Okay, so that means we have to push a breakpoint earlier.
Is it because you didn't do return instead? You did 0 instead of return for that second question?
Well, this is right before the add the call. This is right before we call add. Let's take a look at the stack right now. This is set up correctly. This is the address to the return value. This is the address of 0. This is the address of 0, and the rest.
So in add, you've got a waylay pop somewhere in add. It's getting rid of that BF, that force.
Okay, look at the stack pointer. The stack pointer is actually off. So I think the debugger. Okay, I think I know what's going on. What does the debugger know at this point?
That we're missing something.
No, the debugger actually understands what add does. Right? Because which programming language did I use to write add this time?
Oh, C.
I use C to write add, right? And the debugger understands that we have just called add. So I am thinking that the debugger is automatically cleaning up that part of the stack. And that's why the stack pointer is actually off at this point.
But we did not include Skynet. It's learning.
Because there's no way to explain it. I mean, there's no way the stack pointer can be off by 4 bytes. And we are not copying that correctly, so that's why we have a problem. I'm going to find out exactly what the problem is, and then on Thursday we'll go ahead and fix it. That may not be a problem at all. It could be just the way I run the debugger that's causing the problem.
So is there a homework assignment?
There will be a homework assignment. I'm going to do it in the lab, so I will make the assignment in the lab.
Will it be available by the time we get home?
It will be available by, well, it depends on whether people are interrupting me or not. If there are no questions, it will be up by 9 o'clock or so.
Okay.
So you'll be done by 10?
No, I'll be done by about an hour before class.
Yeah, that's about right.
Is the homework due Thursday? This Thursday?
The homework is due next Tuesday. You have 1 week to do it.
Okay, next Tuesday.
Yep.
Just making sure there's no sign-in sheet.
There's no sign sheet today.
Cool.
See, this is what happens when you don't get compilers.
This is what I've been doing since 1990.
Oh,
20 years.
good times.
Yep. Yeah, I used to write compilers.
Oh, okay.
Yeah, it's not anything like GCC. It's a very kind of archaic, old C compiler.
Right.
But just maintaining that thing is fun. Trying to sneak in changes. When my supervisor is not watching, that's fine. What kind of stuff am I sneaking in? Type checking and other important stuff that C should have.
Oh, really? Huh. Have you heard of Amtel's VUSB library?
Say it again.